So in this problem, we're going to practice writing the equilibrium constants. So anytime you have gases, you got to worry not only about Kc, which is in concentration units, moles over liter, but you also have pressure because gases exert the pressure besides having a concentration. So we can do Kc and Kp for these when there's gases involved. So for part A here, products over reactants. So let's do a Kc first. It's going to be the concentration of CO squared divided by the concentration of O2 divided by the concentration of CO2 squared. Okay. And also because all of these are gases, we can also express this as a pressure. This would be the concentration of carbon monoxide squared times the concentration of PO2 raised to the power of 1 divided by the concentration of CO2, and we square that. Okay. So obviously the law of mass action tells us that this 2 becomes the square. That is the definition of the law of mass action. We can also substitute things here because Kp, according to our textbook, is equal to Kc, and that whole thing is multiplied by RT raised to the power of delta n. So delta n here would be 2 plus 1 is 3, 3 minus 2 is 1, so delta n is 1, and RT would be raised to the power of 1. So we can manipulate like that to get Kp if we're given Kc, or vice versa, the Kc here. It would be O3 ozone squared divided by concentration of O2 cubed. All right, so that's one way to write it. But again, I want to emphasize because we're talking about gases, we can also do this in terms of pressure. So in that case, it's going to be a Kp, where the Kp, the P stands for pressure, and that's going to be the pressure of O3 ozone squared divided by the pressure of O2 cubed. Okay, and then you can mix and match them. So again, Kp is equal to Kc RT to the power of delta n. What would be delta n for this? So delta n, we have 2 moles here. 2 moles minus 3 would be minus 1. So this delta n would be minus 1. So Kp would be Kc, and RT, that whole thing is raised to the minus 1, which is the same thing. Now, this is a little bit of extra math here. RT, that minus 1 takes it to the denominator. Okay. Well, we already know what Kc is. We can plug it in here. We know what Kp is. We can plug it in here. Basically, if we're given one, we can solve for the other. So all of these can have a Kc concentration or Kp pressure. Don't forget the exponents here. So that's going to be cubed. And the only thing here that's a little bit different would be this one. These are aqueous, so this will only be expressed in concentration. So products over reactants. Part E will only be in concentrations. Gases, again, can be in concentrations or pressures. And again, don't forget we omit solids. So let's just quickly do part D. Here, D, let's express it in terms of concentration C. It's going to be CO times H2. Okay, each concentration raised to the 1 power, because hopefully this is a balanced equation. It is balanced. And divided by H2O raised to the 1 power. Okay, Kp would just be pressures because this is a gas. That's a gas. That's a gas. So this could be Kc or Kp. Omit solids. Solids just do not go into an equilibrium expression. Solids have a density. They don't have a concentration. We also do not put liquids in there because liquids are generally the solvents, and the reaction is happening in the liquid. It's happening in the solvent. So that's not the liquid is the medium in which the reaction proceeds. So we don't add it. So, and again, no liquids, no solids into our equilibrium expression. Equilibrium, be cognizant now. Arrows going in both directions. That is, at the end of the reaction, at the end of its completion, we will have some reactants left over and some products left over. Whether it's more products or more reactants, whether it's more reactants over more products, that depends on the magnitude of the equilibrium constant. Obviously, if you have equal reactants and equal products, at the end of the day, when the reaction is done, the equilibrium constant will be 1.